Anybody who's really seen it has a different view than people who haven't. There's something very eerie, very strange about this process. It's almost impossible to believe when you first really look at it. If you see your first brilliant display of the aurora, it's like, how can this actually be?
If you see the aurora, it's very dynamic. It's full of motion, structure, curtains, flicker, pulsations. All these things have ultimately physical causes that we don't quite understand yet.
Auroral studies is really driven by two motivating influences. The first is, I like to think of it as curiosity-driven science. On the other hand, there is very specific effects of the aurora. It has, in the past, caused power systems to quit. There's communications aspects to it, as well as navigational aspects that one has to be concerned about. And if there's going to be a tourism industry, you can imagine a space tourist might well want to see the aurora from space. It potentially is a source of danger to astronauts. Space weather is still a bit of a mystery. It's not nearly as well understood as weather is down here where you and I breathe. But if we're going to become a spacefaring nation, we have to understand space weather, just as the seafaring nations, 3 centuries ago, had to understand the weather that we have.
In the bleak Arctic tundra of northern Alaska stands a rocket range only used every few years. On these rare occasions, scientists risk multi-million-dollar payloads of experimental equipment that they launch directly into the Aurora Borealis. These rockets explore the electrical processes that cause the northern lights, a phenomenon only partially understood after decades of study. The rockets can only be launched when the weather is clear and the aurora is strongest, usually the first 2 weeks of March.
How many axes do we have?
Two.
That? All right, well, we're looking at
two separate... north, south, and east, west.
Okay, all right, well, I don't know which one's north, south, and east, west.
Which is north, south, and east, west.
All right, but it looks like we've got...
Paul Kintner, the world's most experienced auroral rocket scientist, is hours away from his 33rd launch.
Monochromatic.
Okay, so it would be 10 data points.
Nearly 35 years after his first rocket, Kintner's passion for studying the aurora has not abated.
PI2. You've seen PI2 before? It gets me up every morning, gets me to work, and it gives me the endurance to get through these tough campaigns in cold and windy locations. And it keeps, I guess most importantly, it allows me to keep taking these risks.
We're at 3 hours and counting for Lynch on pad 4. I'd like station checks on channel 2, please.
Go. Is Mark up there with you now?
Range safety is go. TM.
What are the temperatures like today?
Turn the payload on here was 67 up in the TM section.
Okay. Is the snow going to cause any problems for us? Is that something you worry about?
Us here? No.
Yeah, okay.
Kintner does some last-minute consultation with the NASA team, which has come to test, assemble, and launch his rocket. It will deploy 5 synchronized probes that will measure the electrical fields inside the aurora, giving a 3-dimensional picture of the unstable energy there.
The reason we study the aurora is not just simply because it's beautiful and it's captivating, but it's one of the few opportunities to understand the cosmos in our own backyard.
Between 100 and 800 kilometers above us, the aurora shimmers across the upper atmosphere, also known as the ionosphere. This phenomenon has its origins in the sun's outermost layer, or corona, a fiercely glowing halo of 1,000,000 degrees Celsius. At these temperatures, electrons are torn off of atoms, creating a soupy gas of charged particles known as plasma. This plasma is too hot for the sun's gravity to hold it down, so it constantly billows away from the sun as the solar wind. Some of it comes towards the Earth at more than 1,000,000 kilometers per hour. Near Earth, the solar wind runs into the Earth's magnetosphere, which shields life on the planet from the dangerous solar particles. Still, a small part of this energy reaches the upper atmosphere, or ionosphere, and forms an auroral oval around each of the poles. When the solar particles hit the ionosphere's gases, mainly oxygen and nitrogen, they excite the atoms, which give off light in characteristic colors, mostly green, but even the occasional blue and red. Although we understand the basics of auroral science, there's still a lot we don't know. Kintner risks his multi-million-dollar rockets to find the answers.
I have, as well as some of my colleagues, have stopped the count under 30 seconds because we didn't think the aurora was going to stay. And that gets everybody really nervous. Christina, pay attention. Yeah, this way. Thank you.
NASA officials have never allowed Kintner and his colleague, Christina Lynch, this close to a live rocket.
This is the fun part. Why do you look serious?
Launching the rocket is not an enjoyable experience. It's a gut-wrenching experience. That's nice. They actually have now. There's a couple of $1 million involved. And if one makes a mistake, I've done it once in my lifetime, if one makes a mistake, one has to come back and explain to everybody why there's no data.
This is 2 proposals, 3 years.
3 years?
Yeah.
All for 10 minutes.
But it'll be a good 10 minutes.
Ah. Okay, the lights come down. That looks good. Let's see.
To make Kintner's experiment work, the rocket must fly directly through the fast-moving curtains of an active aurora, which can disappear as suddenly as it appears.
That launch decision? Oh, that's just gruesome, trying to make that launch decision. Everybody is sort of unique in how they do it. Some people spend all of their time just looking at data from satellites and looking at data from ground sensors. I like to go outside and look at the aurora. People say I'm sort of old-fashioned, but I still like to go out and look at the aurora, and I've had enough experience now doing that as I can generally tell what it's going to do 10 to 15 minutes in advance. In fact, it can completely disappear in a 10 to 15-minute period. So one has to make that decision that the aurora is going to be in the right place, it's going to have the right characteristics, and it's not going to leave. That's what makes it so gut-wrenching, is trying to make that prediction.
Payload control, you go?
Go.
Radar?
Go. Check 40, 41, 43.
Flight vehicles, you go?
Go.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.